I welcome you all in this presentation related with the subject fundamentals of surface engineering, and we are talking about the adhesive wear, its mechanism and different factors that affect the adhesive wear. So far we have talked about the mechanism of the adhesive wear as well as the various surface and material related parameters that affect the adhesive wear behavior of a material. We have left with one topic or one parameter related with the adhesive wear which affect the wear rate or the wear behavior. So, that parameter is basically that parameter is the type of the relative motion, type of the relative motion. So, type of relative motion, which means what is the nature of the component which is under consideration movement with respect to the counter surface. So, this is the if this is the component 1 which is being considered and the counter surface is this, then this movement is a reciprocating type or unidirectional type. These are the two possible situations, whether it is reciprocating or unidirectional movement type. In case of the reciprocating movement, like say in the top view, if we see this setup, then the movement of the component over the counter surface will be in both the directions like this. So, the wear track path will be repeated in the case when the reciprocating movement is involved, and this kind of the movement is typically observed in case of the piston and cylinder assemblies. But there is another kind of the movement wherein you will see that the movement is unidirectional. So, in that case this is the counter surface and this is the pin. So, the pin keeps on moving in one direction only, it doesn't change reverses its direction of the movement. So, in case of the unidirectional relative movement, the direction of the movement remains one and single. So, what is the implication of the relative movement of the component with respect to the counter surface? So, that is what we will be seeing now. So, here if we see if this is the component and this is the counter surface, and if the reciprocating movement is taking place. So, under the adhesive wear conditions and when the reciprocating movement is taking place, obviously the wear particles will be formed due to the adhesive wear in course of the sliding or in course of the movement, and these wear particles will remain for a while between the matting components, and these will act as a third body. So, since most of these wear debris and wear particles are harder than the respective base metals, and and this hardening happens means their hardness is increased because of the work hardening effect. So, fine and hard particles present between the two components which are under the relative movement, these act as a third body, and because of their hardness greater than because of their higher hardness than the respective base metal, sometimes these also act as a these facilitate the abrasive wear. So, under the reciprocating movement, when the wear debris particles are present between the matting components at the interface, presence of such kind of the hard particles, sometimes they act as a third body and cause the abrasive wear of the component. So, obviously the abrasion will happen more in the component which is softer. So, if the component 1 is softer, then it will be subjected to the more abrasion as compared to the another component. So, this is one phenomena that in case of the reciprocating movement we may find more wear rate, higher wear rate as compared to the unidirectional movement. In case of the unidirectional movement, like say in this particular situation where this is the wear track and this is the pin. So, the disc is moving and the pin is located at a particular position. The movement of the disc counter surface with respect to the pin will be continuous movement, will be generating the wear debris at the pin and the counter surface interface, and these wear debris particles under the effect of the centrifugal force will be thrown out of the wear path. So, chances for the presence of such wear debris particles at the in the wear path or wear track, that those will be minimum, and therefore, the chances for the wear debris particles to act as a third body will be less in case of the unidirectional relative motion between the components. So, this is how we can compare the type of the relative motion and its effect on the wear. So, in case of the reciprocating movement, possibility for presence of third body between the matting component is more as compared to the case of the unidirectional relative movement. Now, another point regarding this is the type of the contact. So, there can be various types of the contacts, like it may be the flat surface is sliding over the another flat surface, like this is typically observed on the lathe machine guideways. So, in this case one flat surface is having the movement over the another surface. So, back and forth movement takes place in this particular case. So, this is one where the entire load is transferred through the interface over a larger area. So, actual contact stresses in this case are very less as compared to the case when the other types of the contacts exist, like the curve and curve kind of the contact which normally takes place in case of the gear tooth contacts, like these are the gear tooth present on the two gears meshing with each other at this particular point, since both surfaces will have the curve. So, these will be having the curve contact. So, contact will be along a particular line. So, it will have the line contact. So, in case of the line contact, the stresses will be more localized as compared to the case when the entire surface was in contact with the counter surface. And there can be another possibility where one ball is in contact with the another curved surface. This happens in case of the ball bearings. So, where ball is in contact with the curved surface like bearing race, in this case it will be point contact. In case of the roller bearing, it will be the line contact. So, there will be a surface, there will be line, or say there will be point contact. So, the area of contact will be different in all these three cases. So, accordingly the actual or the true stresses at the contact location that will be varying. So, especially in those cases where the point contact exists, in case of the point contact the true stresses or actual stresses will be much higher as compared to the case when there is a line or the surface area contact. And because of this, when the stresses are too high, true stresses are higher, then we can say the contact, actual contact area will be higher, while in other cases when the true stresses are lower, then due to the limited stresses, the extent of the deformation of peaks and valleys present at the surface layers, that will be limited. So, the actual contact area will be less. So, if we see, since all surfaces will have some kind of the peaks and valleys at the surfaces, and when the contact stresses are high, then these will be collapsing and forming the greater actual contact area. Direct metal to metal contact area will be more, and this will be causing the more the friction and wear related problems if the proper lubrication is not carried out. So, effective lubrication will help to avoid the direct metal to metal contact, and thereby it will be facilitating the reduction in the friction and the wear behavior of the material. In case of the ball bearing and roller bearing, we know that since the contact area is very less and the lubrication is very effective. So, this helps in having the relative movement at very low wear rate and very low with a very low frictional effects. So, adhesive wear is represented through one of the very classical Archard's law on the adhesive wear, and according to this what it says, that volume of the material lost by the adhesive wear V in meter cube. This is given as V is in meter cube, can be given by the K is the proportionality coefficient, and L is the load in Newton, and the D is the sliding distance in meter, and the flow stresses which will be determining the extent of the plastic deformation at the surface, which is given as a 1/3 of the hardness. So, H is in the PA Pascal, and the load is in Newton, and this distance is in meter. K is the wear coefficient. So, the volume of the material loss V is given as actually proportional to the normal load which is applied and the sliding distance, while the wear volume is inversely proportional to the hardness of the material. So, this coefficient 3 is since the flow stresses are approximated with the help of 1/3 of the hardness, when the hardness is expressed as in PA unit. So, this wear volume is inversely proportional to the hardness of the material, which means the increase in hardness will reduce the adhesive wear. Similarly, the increase in the normal load and the sliding distance will increase the adhesive wear proportionally or linearly. So, normally what is observed according to this one, for the different materials, although trend may vary significantly. So, the load in general increase in load increases the wear volume, same is true for the increase of distance increases the wear volume, but this happens especially under the mild oxidative wear condition. For if there is any change in the wear mechanism from mild to severe, then there will be another wear rate through which which will be governing the wear volume. So, when the wear rate is increasing linearly up to a limit, and thereafter there will be sudden increase in the wear rate beyond a certain point, which will be suggesting that there is a change in the mode of wear, and now severe metallic wear mode has started. Similarly, if we see the hardness of the material, which if we can increase through the different thermal processing and mechanical methods, then for one material as a function of the sliding distance, if we see for one material having the one level of the hardness, and for another material wear may change through the another level. So, in y axis if we have wear volume, and in axis we have sliding distance, then for same material of one hardness value will be subjected to the wear at one rate as compared to the wear of the material wear of the same material, but having the another hardness. So, H1 H2 is representing the different hardness values of the same material, which is achieved through the different processing routes, maybe thermal method or the mechanical methods, which may be in form of like burnishing or heat treatment or nitriding, etc. So, any kind of the method which can be used for regulating or for achieving the required hardness. Now, so this was the Archard's law, but most of the time we do not see that the variation is that linear for the hardness. Means the wear volume is not exactly always inversely proportional to the hardness. Sometimes we may have the different kind of the various trends of the variation in wear volume as a function of the hardness. So, this law not necessarily will be following under all situations, but this is a classical and original law which was derived to understand how the different materials will behave if their hardnesses are if they are having the different hardnesses. If we see, if we take like say the 4 different materials of the different hardness values of like say the 20 RC, 30 RC, 40 RC and 50 RC, and then we try to see wear behavior, we may find that there is some kind of the consistency with the increase of the hardness, there is a reduction in the wear volume. So, for under the simplified conditions, normally this law behaves like this, where the wear volume is found inversely proportional to the hardness values. Another interesting aspect is this wear coefficient, coefficient which is basically V equal to the K L into D divided by H. So, K is basically the wear coefficient K which is obtained through V into H divided by L into D. So, this gives us a very interesting parameter which indicates the different bands for the different kinds of the wear, and normally for adhesive wear under the well lubricated conditions shows the wear coefficient value like say 10 to the power minus 9 to 10 to the power minus 12, while for under the dry conditions it is lower, maybe like 10 to the power minus 5 to 10 to the power minus 8. For abrasive wear, it is like say 10 to the power minus 3 to 10 to the minus 4. For erosive wear 10 to the power minus 2 to 10 to the power minus 3. So, very high erosive wear rate and abrasive wear rate can take place. So, the two body abrasive wear offers very high wear rate as wear coefficient as compared to that of the lubricated and the adhesive wear under the dry sliding conditions. So, normally the wear coefficient is found at 10 to the power minus 3 to 10 to the power minus 12 depending upon the wear rate. Most of the engineering components under the adhesive wear conditions are designed to have the wear coefficient in the range of like say 10 to the power minus 10 to the 10 to the power minus 12. While erosive wear like solid particle erosion or the slurry erosion, under those conditions we experience the much higher value of the wear coefficient. Now, we will be going through the another type of the wear that is basically about the abrasive wear. This which we can understand from this tribological system, as I have talked yesterday about the Tribo-system. Here this is say component 1 which is under consideration, and it is in contact with another matting component 2, and between the two components some kind of the separating field may be in form of oxides or the lubrication or the steam or something else is present. So, this is what we can say the substance or the material which is present at the interface, and then this system will be working in particular environment, so that we can see surrounding and its temperature, humidity, all that will be important from the wear point of view, and then we will see the particular kind of the load is being a service load which is being transferred during the service from one component to another, and the kind of motion which exists between the two components. So, these are the 6 different components. Component 1 and 2 are the parts which are interacting with each other. There is one something which is present in between the two, so that they can be isolated from each other to avoid the direct metal to metal contact, or some other kind of particles are present, like in abrasive wear these can be there in form of the particles. So, these are the typical Tribo system. Now, if you have to understand the abrasive wear, then for understanding the abrasive wear is basically here we can see abrasive wear, which is very commonly observed in those industries where hard particles they are rubbed or forced to pass through the surface of the component. So, it can happen like all those components which are used in the mining industry, those which are used like drill tools used in petrochemical industry for exploration, drilling the hole, and it can be there in the field of the like earth moving components like excavators, which are used for digging the soil and for creating various types of the constructional features. So, this is basically used in the construction industry. So, wherever the hard particles are forced to are rubbed forcefully against the other components, we will be seeing that some kind of the abrasion is taking place. So, rubbing of the hard particles with the metallic pieces basically causes the abrasion. So, there can be the two types of the abrasive wear behavior, means the two types of abrasion. One is the two body abrasion, and second is the three body abrasion. In case of the two body abrasion, like this particle is being rubbed over the another surface of the another component. So, this is basically one component which is being rubbed or which is being abraded by the another hard particle. So, this is the particle which is being rubbed. So, this is the situation of the two body abrasive wear, and in case of the three body abrasive wear, between the two components third hard particle comes in between. So, it causes the abrasion in both or one of the two, whichever is softer. So, this is the situation of the three body abrasion. And this is typical, this is the case similar to that of the like metal cutting or grinding, where like in grinding wheel various abrasives are fitted and these are rubbed against the workpiece. Similarly, in the three body abrasive wear, this is like the hard particle enters in the bearing system. So, between the one roller and its recess, here what we will see that the one hard particle has entered. So, this will be causing the three body abrasive wear. Now, there can be other ways of the classifying the abrasive wear, like the closed or the open type. In closed type, like between the two components, one is forced to pass through, when the hard particle is constricted or restricted between the two components, or like in this in case of the grinding wheel, where abrasive particles are fitted and they are rubbed against the workpiece. So, the relative position of the abrasive and workpiece is very fixed. When this kind of system exists, it is called closed, or between the two components which are closely spaced, third particle comes in between. This is also an example of the closed abrasive wear. And in open one, like over this component, the sand is freely falling over the component. So, this will be the whatever wear will be happening of the component due to the flow of the sand particles, that will be coming in category of the open abrasion. So, this is what we can see from these examples, the two body abrasion where the position of the abrasive and the component which is subject to wear, it is fixed and the two are having the relative motion. And so, this is the two body abrasion, and three body abrasion when between the two interacting surfaces, third particle comes in between, that is the three body abrasion, and when the particles are freely falling onto the surface of the component, then this is called open abrasion. And in this case, what we will see how these will be working. So, in case of the two body abrasion, both in most this two body abrasion is similar to that of the small angle erosion, wherein the material is removed mostly by the metal cutting process, and in three body abrasive wear, particles are loose and they will be moving during the interaction with the wearing surfaces. So, we have already seen the examples of the two body and three body abrasive wear, and its further classification of the abrasive wears and the wear mechanisms we will be seeing in the next presentation. So, now I will summarize this presentation. In this presentation, basically we have talked about the effect of the type of relative motion on the adhesive wear, as well as one Archard's classical law on the adhesive wear, which indicates the effect of the normal load and sliding distance and hardness of the material on the adhesive wear. And I have also introduced the idea of the abrasive wear. Thank you for your attention.